Good morning, everyone. Welcome to this lecture. In this lecture, I am going to discuss the conversion of non-deterministic finite automata into deterministic finite automata. So let's look at first what is a deterministic and what is non-deterministic finite automata. So if I consider the transaction or transition table for an automata which is defined over set of alphabet which is having only two symbols 0 and 1, binary alphabet you can say. So let's say there are two symbols in the alphabet set 0 and 1, and I assume let's say there is two states. This is the initial state and this is the final state. Right? Now for every state, for every input, if there is a one and only one transition is written, then there is a deterministic, otherwise not deterministic. So if I write here, let's say when 0 is coming on Q0, it is on Q0 only. And if I am writing when 1 is coming on Q0, it is on Q0 as well as on Q1 it is leading. That means if it is leading for one input on two different states, it is a non-deterministic automata. Okay, so if it is not leading you towards two states for one input, let's say this is nothing, there is 5, there is no entry. So on Q0, when a symbol 1 is coming, which is a legal symbol in your alphabet, set of alphabet, then also for no entry, we consider this automata as non-deterministic. Okay, so this is applicable for each and every input on each and every state. There has to be unique one and only one entry. Please do remember. So I'm just wiping it out. Now let's focus on the conversion, NFA and DFA. So if I consider there is an automata which is having an initial state Q0, set of alphabet S01 I am taking, and when let's say input 1 is coming on Q0, it is leading you towards a new state, that is Q1. Okay, and when input is coming on Q1, let's say you are reaching to Q2 and assume that Q2 is the final one. The transactions are written something like here it is 0 comma 1, or 1 is coming here, you are going here, and let's say here 0 comma 1, and when 0 is coming you are going here, and there's a loop of 0 and 1. Now this is a non-deterministic finite automata because on Q0 for one input there are two transactions, one on this loop and another is this. On Q1 for 0 input there are two transactions, one in this loop and another is this. Okay, although in Q2 it is fine, there is only one transactions for 0 and 1. So if we do want to convert this into a deterministic finite automata, what we supposed to do is, we first step we need to start constructing a table. So let's construct a table like this. Now in this particular table construction, we need to start this construction from the initial state of the given automata. Okay, so Q0 is the initial state, and we do consider all the symbols, those are given in the set of alphabet. There are only two symbols 0 and 1, so I consider. Right, now on Q0, when 0 is coming, it is leading us only to Q0, but for Q1, this one input Q0 is leading on two different states, that is Q0 as well as Q1. Okay, now what we need to do in this table, we need to write the transaction for each and every set which we are getting here. Okay, so whatever the states we will achieve here, we will write the transactions for them. So in the very first row we got Q0 transactions we have already mentioned. Now we need to consider Q0 and Q1 as a one combined state, and we need to write the transaction for Q0, Q1. In the very initial lectures, I have already told you that a state in the automata or in a machine, nothing but combination of certain variables. So when I'm saying you need to merge or combine Q0 and Q1, that means you are merging the variables as well as the conditions applied on the variables of two different states and defining one state. You can take one example like this. Let's say there is a variable month we have taken, okay, and there's another variable year. So if user is entering, let's say month is equal to 4, that means your machine will predict this is April, right? If your user is entering, let's say month is equal to 5, the machine will predict this is May, right? But if this is so, this variable is helping you to define, let's say, different state. This variable is able to define, let's say, different state. You are utilizing and defining the state. If this year, let's say I'm putting 2023, if I change the value, that will be different year. But altogether, if you want to mix these two variables and want to combine on a single state, so that means you are writing something like wherever month is 4 or year is something. So altogether, the combination of the variable will define a new state. I hope you are getting. So here what we are trying to do is we will combine this Q0 and Q1 and we make a new state. So Q0, Q1 we may write there is a new state and we want to write the transactions for this Q0, Q1. Okay. So for Q0, Q1, if 0 is coming on Q0, you are at Q0. Okay. But when 0 is coming on Q1, you are at Q0, at Q1 or on Q2. So that means when 0 is coming on this particular state, Q0, Q1, you can achieve either Q0 or Q1 or Q2, right? I'm considering the transactions for 0 on Q0 as well as for Q1 and writing it as a combined state. Then for 1, we are reaching to Q0 as well as Q1, and on Q1 when 1 is coming you are at Q1 only, so there will be only 2 states, right? But this Q0 Q1 state we have already written the transactions, so we need not to consider. We got one new state, that is Q0 Q1 Q2, so we write a combined state Q0 Q1 and Q2. Okay, now we write the transactions. So on Q0 Q1 Q2 obviously we will get Q0 Q1 Q2 for 0 input, and similarly for Q0 Q1 Q2 when 1 is also coming we will get same Q0 Q1. So now we did not get any new state, so we need not to consider any new state further. Okay, so how these state has been created, that must be clear to you. Now the next point is, in the given automata that was non-deterministic, there were one final state, that is Q2. Now how many final state we will find out here. Wherever Q0 you are merging Q0 with this particular state, so this state will become final. In this state there is no Q2, so this will not become final, and Q0 was the initial, so it will be initial. So let's construct the new automata. This Q0 is the initial one. Now on Q0, when 0 is coming, it is having a loop, right? But when 1 is coming, there is one state, so I am writing Q0 Q1 kind of a state. Now when 1 is coming, we are leading towards this state. For 1, there is a transaction, right? Like this. Now on Q0 Q1, this is a single state we are considering. There is a loop for 1. So if 1 is coming, there is a loop. But when 0 is coming, there is a new state q0, q1, q2, and this state is a final state also. So when 0 is coming, this state is leading you towards this state. Okay. Now here, when we are having either 0 or 1, there is a loop on the same state. So now in this, if you check for very first state, rather than q0 or this combination, I can give some different name also, because name is just kind of symbol of a state. So instead of writing q0, if I write state A, state B, state C, right? So I may write this is a state A, B, and this is C. Now this automata is exactly equivalent to the given automata, which will generate the same regular language as compared to the previous automata. Okay, but this is deterministic and previous one was the non-deterministic, right? So on A, when 0 is coming, there is a unique transition. For 1, there is only one transition. On B, for 0 as well as for 1, there is only one transaction. Similarly for C. So please do remember these steps. This is very important concept in theory of computation. Okay, thank you. So I'm closing this session. See you in the next class.